Okay, metric spaces. I actually forgot to mention the actual term for this. So I define a metric, which is a function on the x cross x set to the reals. But when you combine the two, then what you've got is a pair of a set and a metric, and it is called a metric space. Okay, so once again, these are three axioms. The two easy ones and one more complicated. Okay. Is what we are facing here. Okay, let's review from last week. The main applications have been the main instances. At this point, we're not looking at this as applications anymore, but rather all of those examples, instances of metric spaces now are covered by one little, really short definition. And now then we will, as long as we can demonstrate that those instances are indeed metric spaces, then whatever theorem we have proven about, or will have proven about metric spaces, will be applicable. Okay, so that's the idea, just the way we did it with groups. So a group is a pair of a set and an operation, and a metric space is a pair of a set and a metric. Okay, so that's the similarity. Otherwise, there is none. So we're talking about algebra versus geometry. Okay, so then that's the first stage, that after the definition is to actually confirm that what we have seen are indeed the metric spaces. We're gonna skip the Euclidean space. Well, I guess that you'll see that in a like advanced calculus course, proving the triangle inequality for the Euclidean space, the Euclidean metric, the standard metric that we're used to. But we will do instead the taxicab metric, which is more exotic, but then simpler at the same time. Okay, so this is what we're looking at. Taxicab metric definition on left. Assume that the first and second axioms are easy, so suppose we already have them. Okay, so now that this is what we're facing, and we tried to figure out last week how to prove that we do have the inequality. And the idea that we ended up with was to use the axiom. Well, this is actually the proof of axiom 1 and axiom 2 here, right there. Now, if we move on to axiom 3, the triangle inequality at the top, some analysis demonstrated that it is ultimately, look at what we want to try to prove here is this part over here. And if you expand it, it is entirely about these differences, those absolute values of difference of coordinates. And if you combine them together appropriately, as I did with the yellow, you have x's and y's separately, and then you should deal with them separately. So that's the idea, and we would rely, for both of them, rely on the axiom 3 for the x-axis and y-axis separately. So that gives me the starting point of actual proof. Once we have the idea, we can just go ahead and try to demonstrate, to have the proof. Okay, so this is the proof. So we have x prime, x double prime in some order on the x-axis. So the order does matter. So think of this as an illustration. So in any order should be applicable. Okay, so it doesn't matter which that order is. Okay, so that's the assumption. And now we use the triangle inequality for R, which is what the x-axis is. Okay, so let's start this way. The x-axis is a copy of R, and it is a metric space. Okay, so we then use triangle inequality, axiom 3, for the metric space for R, this specific metric space. So if we have x prime, x double prime on the x-axis, then we apply the triangle inequality. We have this inequality right there. Okay. So we move on then and do the same for the y-axis. So we notice that the y-axis once again is a copy of R, a metric space. Okay, so then we have, I'm repeating this. If I was typing, I would be doing copy paste. Okay, so then I would replace each x with y, even easier than the right hand. So we have y double prime in some order on the y-axis. Next, we use the triangle inequality. For R, the metric space. Okay, and then we have y prime minus y plus y double prime minus y prime greater than or equal to y double prime minus y. Okay. So step 3, what do we do? What's the next step? You remember? Call this 1 and 2, referring to these two formulas. So there it is here, more or less. Okay, so you see what we're doing? This is where we're supposed to arrive, right? So what do we do with those two inequalities? 1 and 2. What do you do with the inequalities anyway? So these are the only two conclusions that we have. So even if you remember the idea from last week, then there aren't too many things that you can do with inequalities. Considering that triangle inequality is what we're after anyway. So we have two inequalities, and we have to get another inequality. What do we do with inequalities at all that could produce a new inequality? Add them. Yeah. You can add. You certainly don't subtract, but add is the safest thing to do with inequalities and to produce a new inequality. Multiplication might mess it up, but not addition. So then what we have here is I'm gonna then rearrange terms. So x's with rather than going x's with x's. As it is right now, I will be aligning primes, non-primes, and double primes. Okay, so I will combine vertically. Let's combine vertically. So I'll have x prime minus x plus y prime minus y. Okay, so the two first terms of the two inequalities. Okay, and then the second one, two second terms, x double prime minus x prime plus y double prime minus y prime, okay, larger than or equal to. So two larger sides added together larger than the sum of two smaller sides, right? So then I have x double prime minus x plus y double prime minus y, absolute values, okay. And then as you can see, it is not in. Why is it not in the? No, it's fine. Okay. So so as you can see, we are well. In fact, I put parentheses here, even though it is meaningless. But I still want to. There's a point there, right? So I just look at all of these three sets of parentheses, and I recognize each of these terms. So all three come from the same place. What is that? What are these? Well, they take the first parenthesis. What is it? Well, the pictures help just to remember what's going on. This is our picture. Okay, so so as you can see, there's one point at a time. One point at a time. I guess I didn't start quite right here. I should have started with the 3 points. Let me move the proof up here. So proof. So suppose P equal x, y, Q equal x prime, y prime, and R x double prime, y double prime are points on the plane. Okay, so as you can see, the coordinates are appropriately have appropriate attributes, prime or no prime or double prime. Okay, so then we recognize these combined terms as distances, as taxicab distances, right? So x minus x prime plus y minus y prime. So that's what this is. Okay, so this one is from P to Q, and this one is in a similar manner from Q to R. Okay, and the last term is what? What's the last term? The on the right? PR, yes, PR. Okay, so so that picture is kind of a staircase type of a. Did I plot it? A staircase type? Well, I guess not. Let's make a staircase, even though it is not the most general situation. But let's in order to illustrate the idea, it is worthwhile. So like this, like that. P, Q, R. Okay. These are the x's, x prime, x double prime. So I picked the simplest arrangements between the points, so they are going into kind of a diagonal direction. Okay, and then I take on the y, and these are on the y-axis, y prime, y double prime. Right, like this. Okay, and as I said, this will be the first one. Well, the last one. Let's write these first. So I have d p q. That's the first term. The second one d q r. Okay, and that is larger than or equal to. Well, that doesn't fit. That's fine. Larger than or equal to, and that's I have to add more. So let me try to do it like this. This is the straight line for P to Q. That orange line is the straight line according to the taxicab metric from P to Q, from P to R. Okay. So the blue one, and then the orange one. And as you can see, in this particular case, they happen to be equal. Well, we're not relying on the picture to determine what's going on. We have been proving things like this. So that is all solid, pure algebra that we have been doing. But you can see that in theory, these numbers could be the same, not larger than or equal. It's a possibility, certainly. Okay, so and then well, that's the end of it. So let me try to take this picture out in order to to make my point that the proof has to stand on its own, like this. Okay, so the proof is over, and this is an illustration of the proof, of the idea of the proof. Okay, but the proof, as you can see, it is purely algebra right here. Okay, any questions about the proof? So I hope you can reproduce a proof like this on your own. Coming up with such a proof might be a bigger challenge, but at least when you already have seen it once, then that is a worthwhile idea to have in your tool belt. A proof, well, that's what you have inequalities. Then how do you prove one inequality from another? You probably will have to do some algebra of inequalities, and that's what we did. Okay. So okay. So the conclusion is so R2D is a metric space, where D is a taxi cab metric. Okay, so you certainly can just this picture indicates tells you how different the geometry of the space is, because once again this is how you get from P to Q. It is a straight line, or not the full line, but it's a segment. And then the other one from Q to R is once again a straight line, and the orange one is also a straight line. So this is what the straight lines look like. Okay, how you continue on with that one, I do not. It might hard to imagine. So how can you actually build an infinite line in order to have some things similar to what you have in Euclidean geometry? But we're not going to pursue that because we are moving more towards topology than geometry. It is just simpler, so that it relates us to calculus. Okay, so you can certainly think about what a triangle would look like. What does a triangle look like in this geometry?
Has three sides.
Okay, and each of which is what?
Each side has different orientation.
No. What is this? It has a triangle should have three sides. Yes, but what are those? What do those sides look like? What the side is anyway?
Line.
A straight line. And what does a straight line look like? Yes, it looks like this. So what is this? What? It is that it isn't. This is a triangle. P, Q, and R, three vertices of that triangle. That's what the triangle looks like.
So you're saying triangle is made of triangles?
I don't see why. Why is it made of triangles? I don't see any triangles. No, it it has three. It has three sides: the orange one, the blue one, and the green one. Well, green one maybe. I'm out of colors. Give me a good color here. So first of all, what is a triangle? You have 3 points, and they're connected by segments. And we know what segments are. So that's what sides are. They're straight segments, and straight segments are the ones that if you go the shortest distance between the 2 points. So we know that this is how we get from P to Q, and then you can go also and then from Q to R. So the 3 points are here. I think I plotted a little bit. It seems like there's some kind of symmetry here, but there isn't. There is no symmetry here. So maybe let me fix that. They look very similar. So let me fix R a little bit like this. So Q. Let me put R here. This is R. Okay, so, and this is y double prime. Okay, and so the second then okay, so these are the three vertices. They certainly absolutely arbitrarily chosen. Okay, then this is one side. This is from P to Q. It is a segment from P to Q that we're looking at. This is a segment from Q to R. Let me make it black. For Q to R. And finally, the segment for P to R is this. Okay? So it is a triangle, but I was speaking incorrectly. I said the segment from P to Q. What is wrong with that language?
There's two segments.
There are two. What's the other one?
So horizontal component and a vertical component.
Yeah, well, yes, but here it is. In other, just a shorter distance between 2 points. From P to Q, I can go this way, I can go that way. So there are actually two segments of exactly the same length, different segments to get from one point to the other. It sounds, well, first of all, remember, it's taxi cab. So it is really, if you want to get from one point to another, there are always two routes, equally good. Are there more routes? Well, you can go like that. It's just as good. I could go like this. I don't really have too many choices. In fact, in any route through those grid of blocks in the city, I could go like this, and I'll cover the exact same distance. The distance is the same. So all of these are equally good routes. And those all create the same. So different triangles with the same vertices. Many triangles with the same vertices. So it sounds exotic, first of all, but it's not. First of all, it is, once again, that's how you travel in a big city. Second of all, the example that we saw of the sphere, or a circle, of that matter, you can actually start with a circle, even though the more interesting example is certainly the surface of the Earth, but it has the same properties. Well, let's say we're living on a circle. There might be 2 points, if they're diametrically opposite, with two exact same distance ways to get from point A to point B. Say this is P and Q, and there are two exact routes around the Earth to get to the opposite side. So it's not unusual to have that kind of property, that equally acceptable routes from one point to another. So it's just the nature of non-Euclidean curved metric spaces. Okay, so once again, with the this could be P and Q on the surface of the Earth. If you have two opposite ends, you'll have how many routes from North Pole to South Pole? How many routes of the same length? Infinite, right? So just go straight south from the North Pole. Go straight south. You will end up with at the South Pole. Okay, so it is not unusual. It is actually a common feature. Okay, and then there are. So we're not going to go into geometry, even though it's certainly very important to actually see non-Euclidean geometry as it started way back to the problem of parallel, the parallel postulate. Everybody knows what that is. The fifth Euclid's postulate. He was trying to develop his own axiomatic theory of geometry, and he has several. He didn't call them axiom. We call them postulate. And one of the number 5 was that there is only one line parallel to a given line through a point. Okay, so like this. So line, pick a point, then there will be a distinct point. Then there will be exactly one parallel line. Okay. So that was the fifth Euclid's postulate, or Euclid's fifth postulate. Okay, and then they tried over the centuries, people tried to prove it because it was not, because it didn't seem as natural as the rest of them. I don't want to tell what the rest of them are. So anyway, then it was proven that it's impossible to prove, and we have a perfect explanations why it is not possible to prove, because you can invent a geometry which does not have this property. So everything else is the same, except all the axioms are the same, but that axiom does not have to be satisfied. And so once again, on the sphere, I pick a line. Well, first of all, what is a line on the sphere? We talked about that last time. It is a circle. This is a line on the sphere. It is if you want to proceed to the shortest distance, you end up following a circle, but not any circle, but the circle that contains the center of the Earth. So its center is the center of the Earth. Okay, so try to solve the fifth postulate of Euclid on the sphere. What happens? That's a line. I pick a point P. Okay. What happens? What's the parallel line to point P? Parallel to my line.
There isn't one.
What?
There isn't one.
There isn't. You cannot build a parallel line, because once again, for a parallel line would have to be once again of the same radius, and it is tempting to try to build something like this, right? It is parallel. It seems to be parallel, but on the other hand, this is not a circle. I'm sorry, this is not a line, because its radius is small. So if you try to build a bigger one, then its center would coincide with the center of the Earth. It will cross our line. So there are no parallel lines in non-Euclidean. In the spherical geometry, there are no parallel lines. Okay, and then that's one way to fail the fifth axiom. But another one is to have not too few, but too many parallel lines. So there is hyperbolic geometry, which has infinitely many parallel lines built. So hyperbolic geometry, if you can imagine hyperbolic paraboloid, you know what that is, right? So and you try to do geometry on it, then there will be infinitely many parallel lines. So that's non-Euclidean geometry in a nutshell. Okay, so we're not going in that direction, because there is more to it than just these axioms in order to have a fully developed geometry. We go in the opposite direction, what is called topology. So there is nothing else to worry about, just the metric, and our interest will be in a minute will be convergence, convergence of limits. So limits and sequences in their convergence. But before we do that, so we set this aside just as a note. So unfortunately, to find the non-Euclidean geometry, where do you would be? I can think of a class that you have to take that would teach you non-Euclidean geometry. Unfortunately, so even though this seems to be very central to the history of mathematics. And that's how you build how you're going to do modern physics without the curved non-Euclidean geometry. Okay, that's how it happens. So it's extremely important. But it is also complex. So we're not going to be doing it. Let's just proceed to more metric spaces. And another example, it's almost as simple as that, is graphs. Okay, so metrics on graphs. So as an example was very informal. So A, B, C, D, E, and then there are edges. Some 1, 2, 3, 5, 7, 1. Okay, so that's a metric on a graph, which is, in other words, it is a weighted graph. So to each edge, a weight is assigned. and the weight is simply a number that is positive. Okay, that's it. Okay, so that's an example. So we can't certainly just go straight ahead and study this as stated, as weighted graphs. But I wanna just have this as an exercise to actually understanding what a graph is. So anybody knows what a graph is based on this? What is a graph? So I want to interpret graphs as we understand it. It is a network connected by edges. Very simple model. How do we interpret it as in the way we have interpreted everything, as is in the set theoretic way. So there is a set somewhere, and there might be some kind of a extra structure on it. So we are not talking about weighted graph, just a graph, which means the same thing without numbers. So let's start with that. Here's a graph. So how do we interpret this in a set theoretical way? What is a graph? Now let me get you started. Suppose there is a set X, and so here is the set is A, B, C, D, E. That's my set here in this particular example. It is just the nodes of the what's called just a word used in graph theory, nodes of a graph. Where do they come from? They come from just a set. So we have a set X given to us, and then we build a graph on top of this set. So, what is it? So, let me point out, so we already have X. This is X. So that has been taken care of. Well, I'm not sure if everybody has equal experience with graphs, and that is, the drawing is not important. Okay, so it is not on the plane or on a piece of paper. It is purely a set, and so it is a list of elements of a set. It could be points, could be people, any kind of attributes, anything that you can imagine. Just any set can be turned into a graph. Okay, so in fact there's a bunch of examples. The question now becomes, how do we add edges? What are edges? So a simpler question, what is a graph? We already have started. There's a set X. What are the edges? So these are the edges. So but what are they? How do we explain them in a set theoretic way? Well, one at a time. Let's try one at a time. So, an edge from A to B. What is it? Any thoughts?
You said an edge, right?
Yeah. How do you record? You have a list of x's of x, the nodes. Okay, how do you add to that list a list of edges?
When one before it is included and the one after it is not? In the set?
No, I'm not sure what you're saying.
If you're right on the edge of the set, if the one before it is included in the set and the one after some value is not included.
Well, the list is this, right? So this is my list of x's. Now, how do you list? Let's try to list edges. Let's call, well, unfortunately, it's the same letter, so what is the letter say? I don't know why. Yes, okay. Let's list edges.
I thought we were looking between A and B.
Right, well, yeah, so I'll put the list A, B on the list to begin, and then I need the rest of them too. Okay, so I just listed BC, AC, AE, EC, CD. Okay, this is just a list of edges. But set theoretically, what are these? No, there are no distances. So once again, we are concentrating on only this part, so there are no numbers. We'll get to weighted graphs later. Let's just look at what graphs are. AB, what is AB? It is a pair of nodes. So these are pairs of nodes. In fact, it doesn't matter. We assume that there's only one edge between any 2 points, so it doesn't matter. AB is the same as BA, by the way, so like that. There is an edge there or not. It's like once again, a network. So what I'm driving at is where S is a subset of what? Pairs of nodes. How do we form pairs in set theory? As we have recently, very recently. How do we form pairs?
Addition?
What?
Addition?
No. Pairs of elements of a set.
Is it like the sides?
S
Like AB is a side, BC is a side.
Sud?
Sides of the little shape thing you drew.
No, I don't think. Okay, let me try to do it this way. Okay, so this is how I would try. If I had a spreadsheet, for example, this is how I would do it. I would put a list of the nodes first, okay, and then okay, so that's the list of all my nodes. How do I point out the presence of an edge between A and B? Well, if I have a list like that, well, very simply, I have another list of the same elements, and then what do I do? How do I point out the presence of an edge?
Two elements that are not the same?
Yeah, but as you can see, there is no ED, for example. Look at it over there on the picture. ED is not every edge has to be present. You can have no edges. It's still a graph. So AB is present. What do I do on this table to point that out?
Oh, -1, 0,
No, I just take this row and this column and put an X there. So if an X is there, there's an edge between them. And since because A and B are AB is the same as BA, I'll have two X's at a time. Okay, and then I'll keep going. So I have AC as well, and CA. And then I have AE, EA. Okay, so let's, what else is there? BC. BC is this. BC and CB. Okay, CE and EC. Like this. And finally CD. Which is this, CD and DC. Okay? This is the graph. It is literally could be thought of as cities, and you list the cities, list of cities, and then you indicate whether or not there is a road between them, a direct road. Okay. If then you proceed in that direction, what you do is if we want to study metrics and distances, then instead of those crosses, I'll put numbers there. Say if I'm concerned with distances, say 50 miles between city A and city B. Okay, so depending on the theory that you pick, on the diagonal you may or may not have anything. It doesn't matter really. Is A connected to itself or not? It doesn't matter. Okay, so it depends on the point of view. If we're studying weighted graphs, we certainly and there is an edge from A to A, then its weight should be 0 anyway. Otherwise what? If there is an edge from A to A, what should be the weight? It should be 0 because why so?
It's the same point.
Yeah, and can you justify it? Remember, the justification is the first axiom of metric spaces, which is what we are ultimately aiming for here, is to see that this is a metric space, and remember the distance from point to itself should be 0. That is why all the weights should be all positive unless you are moving to yourself. Then it should be 0. Okay, so this is a graph. It is pretty much a table of a square table of the elements of the set. Okay, and with marks indicated wherever that edge is present. However, we have to have. Well, I still need to put something here. So that's a very convenient explanation of what this is, and that this is how you would do it, whatever while you're studying graphs. But there is a set theoretic explanation. Still, I want to, since it's such a big deal in this course, there is a way to explain what is this. What is this? What is this table? A's on the rows, the rows and the column also A's. So each cross corresponds to a pair. For example, this cross corresponds to a pair CD. Each of them is an element of our set. So once again, that question is, what is this? Edges are subset of what? What? An edge is an element of what? An edge is a pair of vertices. Where have we seen pairs, a pair of elements of X? Where have we seen that recently? So this is X, and that is X. So this is altogether, what is it? Pairs of X, of elements of X. No. Let's say we are looking at all possible edges. All possible edges means that we have all possible pairs of elements of X. Okay, for each of the entries in this table. X cross X, right? That's what it is. X cross X. That's what we're talking about. Pairs of X. So we have a set. And then we have a subset of the Cartesian product of X and X. That gives you a graph. Okay, the only requirement is it is a non-oriented graph, then AB. If AB belongs to it, then so does BA. So a graph, at least there are several definitions of graphs, but one is a graph is a graph on a set. X is a subset of X cross X, such that AB belongs to X cross subset say E, because these are edges. If AB belongs to this set E then BA also belongs to that set E. So that's one way to define the graph. So that subset E is stands for edges. So X is the set of nodes to begin with, and then there are some edges between some of these elements. Okay, so either you illustrate it with that picture, a network type. The mutual location are indeterminate. They're absolutely like with sets. There is no order between them. The only relation between the nodes are the edges. So you could rearrange these terms arbitrarily as long as you can have edges between them, and you have it. So so that you would not be tempted to actually think about a graph as something physical with attributes that aren't there. That's why we use either a table like this, or we're just going all the way to set theory. It is X cross X, the set of pairs of X. And then if you take the whole thing, then there is an edge between every two nodes. It is called a complete graph, and well, certainly they're separate, smaller subset, small topic. So we just look at the graph of as the set of on a set as a subset of the Cartesian product of X and X. Okay. So so that's a graph, and then what remains is just to assign to each edge a number, a positive number. It ends it. You have yourself a weighted graph. So next time we'll just look we'll demonstrate that it is indeed a metric space. Okay.